All right, let's dive right into episode 2.3 of our explainer series, Corrosion Prevention and Control. Today, we're unpacking the slow chemical attack. Unlike erosion, which literally scours away metal, a chemical attack doesn't need a single grain of sand to destroy your pipeline. It just needs carbon dioxide, water, and time. And here's the really uncomfortable truth about field life. A pipeline that gets validated as perfectly safe in year 1 can silently become a massive liability by year 15. When a well is fresh, you've got high pressure and a low water cut, meaning there just isn't much water in the fluid mix. But as that reservoir matures, the pressure drops and the water cut climbs. From topside, production might look completely normal, but deep inside that pipe, the risk profile is shifting dramatically. To actually understand this shifting risk, we first need to define the threat itself. In the industry, this is known as sweet corrosion. It happens because carbon steel, which, let's face it, is the economic default material for most subsea piping, is highly vulnerable to produced water that's loaded with CO2. We call it sweet corrosion just to distinguish it from sour corrosion, which involves hydrogen sulfide. But don't let the name fool you, there is absolutely nothing sweet about what it does to your infrastructure. So, how does this actually operate in practice? Well, think of CO2 corrosion like a can of soda left open on your kitchen counter. When the can is fresh and sealed, it's totally stable, but the second you leave it open and exposed, the CO2 keeps slowly reacting with everything it touches. Produced water with dissolved CO2 does the exact same chemical work on steel, just over years instead of hours. Chemically, this builds up through a relatively slow process. First, the CO2 dissolves into the produced water. Next, that dissolved CO2 hydrates to form carbonic acid. This drops the pH of the water, turning it into a weak acid that aggressively eats into the carbon steel wall. And over time, instead of just a uniform, even loss of metal, this often forms localized pits. These are essentially deep craters that can rapidly compromise the structural integrity of your entire pipeline. Section 1. Predicting the damage rate. The DWARD model. Obviously, if we can't predict this, we can't manage it. The absolute industry standard for predicting this degradation in carbon steel is the DWARD CO2 corrosion model. This set of equations, often used alongside industry codes like the NOR6 standard, shows that your corrosion rate hinges on 3 main variables. First, the partial pressure of CO2, which is basically just how much CO2 is in your system. Second, the temperature of the fluid. And third, the pH of the water. Engineers use these exact factors to calculate, down to the millimeter, how much steel is going to be eaten away each year. But what's absolutely wild about this model is its extreme sensitivity. We're not talking about a simple one-to-one linear relationship here. If you turn up the dial even slightly on any of those 3 variables, you get a massive, disproportionate jump in how fast the acid eats the pipe. A slightly hotter fluid, or just a marginally lower pH, can literally push your system from a mildly corrosive regime into a highly aggressive one overnight. To put some real numbers to this, let's look at uninhibited CO2 corrosion rates. That means what happens if we do absolutely nothing to protect the steel. In mild conditions, this chemical attack might steal less than 1 millimeter of steel a year. No big deal, right? But if you have aggressive conditions, meaning high CO2 partial pressure and high temperatures, that weak acid can strip away well over 5 millimeters of steel annually. At that rate, a standard pipeline would be completely eaten through in just a few short years. So let's do a quick mental check to see how this ties back to field maturity. Imagine you have a well where the water cut shoots up from 10% to 70% over a 15-year period. However, the actual concentration of CO2 in the gas stays exactly the same. Based on what we've just discussed about the mechanics of sweet corrosion, what do you expect happens to the overall corrosion rate of that pipeline? The rate climbs. And it climbs significantly. Why? Because water is the crucial medium for the chemical attack. Even if the CO2 levels don't budge at all, a higher water cut means that more water is physically in contact with the pipe wall for much longer periods of time. This increases both the total duration and the surface area of the chemical attack, meaning your corrosion management strategy absolutely has to be planned for end-of-field conditions, not just day 1. Section 2. Defending the pipeline. Upgrades and chemical shields. Since the threat scales dynamically over the life of the field, we have to intervene. We essentially have 2 choices to keep wall thickness loss within safe design limits. Option 1 is a metallurgical upgrade. This means ditching standard carbon steel entirely and using a corrosion-resistant alloy like 13 chrome or duplex stainless steel. We do this when the predicted corrosion rates are so extreme that no chemical treatment could economically control it. Option 2, if we want to stick with cheaper carbon steel, is chemical inhibition. This requires creating a continuous chemical shield by injecting specialized corrosion inhibitors into the fluid flow to physically coat the inside of the pipe. When it's properly designed and continuously injected, a chemical shield is incredibly powerful. A properly dosed inhibitor program can often reduce the baseline uninhibited corrosion rate by 90% or more. These chemicals basically work by adsorbing onto the metallic surface, creating this microscopic film that completely blocks the carbonic acid from ever reaching the steel. And I need to stress this, that 90% reduction isn't just a nice operational bonus, it is structurally mandatory. It is literally the difference between a pipeline lasting its full 20-year design life, allowing the project to actually be profitable, and a pipeline failing completely in just 3 years, leading to catastrophic environmental leaks and massive replacement costs. Section 3. The danger of silent failure. But listen, relying on chemical inhibition instead of upgrading the metal introduces a massive operational vulnerability because it requires absolute perfection over decades. This is what a lot of people miss when they look at pipeline design. Managing this isn't some one-and-done choice you make at project sanction. It is a relentless, continuous treatment program. Those inhibitors have to be pumped constantly from a chemical injection unit. If your injection stops, maybe a pump fails, or an umbilical gets blocked, that protective film washes away and the protection fails instantly. And the scary part? It fails silently. Operators topside might have literally zero idea that a massive corrosion spike is happening down on the seabed. Fast forward and watch how this builds over a decade. Imagine it's year 1. Inhibitor dosing is completely normal. But in year 5, there's a short gap in chemical injection due to maintenance or maybe some supply issues. Because the water cut is higher by year 5, that short gap allows an invisible, aggressive corrosion spike. By year 6, the damage is already done, but you won't actually know it until year 10, when you finally run an intelligent inspection tool through the line and discover that your critical wall thickness is completely gone. So, how do we combat this slow, shifting chemical attack? Engineers must constantly track the moving target of a rising water cut. You validate your early life flow assurance, sure, but you must strictly monitor your water production. As that water cut climbs, you have to actively scale up and adjust your chemical inhibition dosage to match the growing threat, constantly revalidating for end-of-field conditions. It is a daily, ongoing battle of chemistry and vigilance. So, we've mastered the slow, invisible threat of CO2 corrosion today. We understand the Dewar model, why we have to scale those chemical shields, and the terrifying reality of silent failures. But to wrap up this explainer, I want to leave you with a thought for our next topic. We know corrosion takes years to destroy a pipe, but what feared, solid chemical threat can completely block an entire deepwater flow line in a matter of just hours? We'll dive into the chilling world of hydrates next time. Thanks for learning with me today.